Hello community! So great that you are back. You are not gonna believe it. We have discovered the source of hallucination. We can now say hallucinate.delete. Finally, it is possible in AI. So welcome to my channel, Discover AI, and we have some amazing new research paper on AI. We discovered the source of AI hallucination, and it is breathtaking. And you know what? I'm not allowed to delete it. I'm not allowed to touch it. I'm not allowed to modify it. And it makes me crazy. So let's have a look. Let's analyze what's happened. The hallucination happens in neurons. And we call them H-neurons for hallucination neurons. And if you think, yeah, they're really a particular sort of neuron. So here in blue, you have the normal neuron here and everything is beautiful. But if something happens to this neural architecture, if a particular gap is now detected here, then we have a confabulation engine that is here in high gear, and then we just have an output that is pure hallucination. So we now understand absolutely here the process of hallucination. And it's great. So in what architectural block of the transformer architecture are those H-neurons located? Well, in the neurons, and you might say, yeah, but there's so many different neurons. I mean, what particular neuron now do you mean? I said, well, you know, it's simple. We asked ChatGPT, no? And here we go with ChatGPT 5.1, and it tells me here mathematically, here the neurons in the transformer here, they correspond to the intermediate activations after the first linear layer and before the second layer applied per token. And this sounds good, you know, and I think, I mean, who would doubt here an explanation by GPT 5.1? Because here, all the students are now learning from ChatGPT, you know? But we have learned, hey, as always in AI, we have to validate this explanation by any other AI, so let's do this. And I go here to Amazon Nova Experimental Chat, no? And I ask it, hey, is this a correct statement? Mathematically, here the neurons correspond to the intermediate activation after the first linear layer before the second layer applied per token. And here Amazon tells me, here, hey, we have an input, then we have the first linear layer, then we have the activation function, hopefully a non-linear, and then we have the second linear layer, and then we have an output. And here the mathematical operation here, beautiful. So is this a neuron? And then I have an input is not a neuron. The first linear layer, the pre-activation is not a neuron. And only the activation function is a neuron. And this is great, no? So now we have confirmed by GPT-1, 5.1 on Amazon, this is just here the activation function. And then I go here and I say, but this is complete nonsense, no? To say that a neuron is just a non-linear activation function, explain why. And then I go here to LM Arena here in the battle, and I just some two random brand new AI models, and I say, it's nonsense. And they come back and say, yeah, a neuron is a computational unit that combines the linear transformation with learnable weights and biases and a nonlinear activation function. Reducing it just to the activation function ignores the core mechanism of learning and information processing. And if you look at the other one, it says, yeah, absolutely correct to call out this confusion. The neuron is the whole computational unit, not just one piece of it. Thank you for pushing the precision. This is exactly the kind of rigor needed to truly understand neural networks. And I'm so glad that we now truly understand here the new neural networks. This was an answer by Flashstride, and this was here the answer given by Olmo. So if you learn from GPT systems, well, careful. So, okay, this was here kindergarten, but now to the real stuff. Mathematical reason, a simple multi-layer perceptron can approximate almost any function is known as the universal approximation theorem. Now I asked here just 18 hours ago my community, hey, short question here. Can you write down a complete mathematical framework of all mathematical operations in a feed-forward network in the transformer architecture? And 100 votes. Tell me, yeah, 51% have a deep mathematical understanding of all feed-forward network operations, and 49% say, hey, a short refresh would be nice. So, okay, it's almost 50-50. Great. So I have to do a video on both parts. Okay, so if you would like a short refresh, this is the first half of the video. And if you say, hey, I do have a deep mathematical understanding of all feed-forward network operations on MLP, just give me the new algebra, go to the second half of my video. Okay, let's start. You know, first projection matrix W up of a feed-forward network. Here we have linearity and separability as our topic. Imagine an example, a two-dimensional data printed on a flat sheet of paper, no? And you have red dots in the bottom left and in the top right corners, and you have blue dots in the top left and the bottom right corners. So the task is now to separate the red from the blue using your string cut to a linear plane, and it is impossible. You cannot draw one straight line on that paper to separate them. No? This is because the data are entangled in a two-dimensional space. So what we do? We just project this into a high-dimensional space, like a three-dimensional space. No? Because now you can lift the red dots up into the air, into the z-axis, while keeping the blue dots on the table. And suddenly now you can separate them with a single flat plane. Therefore, patterns that are impossible to disentangle in a low-dimensional space often become easily separable in higher dimensions. So, this is why we have the first projection matrix W up here as a first step in the feed-forward network. Yes, Nano Banana Pro was so kind to print this out for us. So here we just talked about W up. So we have here some information coming in from a low-dimensional mathematical space, and we blow this space up in a high-dimensional space because we want to have a clear disentanglement of all interesting feature of this data stream. And then, of course, in the second half, we will have a reduction coming back to the original dimension of the data stream. But now we have a complete different structure. So let's look at it first. So by projecting W up, we unravel the complex tangled data manifold. We spread here the features out so they are not competing here for the same space. So this gives here the bands or the activation function simply more room to act. And you know that a single neuron, if you have here only a 7 or an 8b parameter model, a single neuron often has to represent multiple unrelated concepts. For one neuron might fire here for the term cats, but also for historical dates. And this is what we call polysemanticity. But when we project to a much larger intermediate space, we provide more neurons that can specialize. No? And this allows the network to assign specific neurons to specific, real subtle features without having to cram too many concepts into a single neuron. And in the early days of AI, you know, the sigmoid and the tangent hyperbolicus, those bands were nonlinear activation functions. They were smooth curves. But then we decided to go with sharp, straight edges, and it was simpler to calculate, to compute a straight line, a straight hyperplane. But now we are coming back here to, in state-of-the-art LLMs here, to Swish or GLU that have actually gone back to the course. So now our bands are curved manifolds again for the separation into subspaces. So, first step, we have projected our input x into a high-dimensional space via linear transformation. Very easy, x is our input, W up is here our matrix or our tensor structure, and we get z. At this exact moment, z is just the rotated, stretched version of x. It contains information, but it has no decision done. No? It just acts as a superposition of all possible features that a neural network could now look for and at. So the activation function now decides when to fire at certain positions. Activation function sigma of z acts here as a gatekeeper. If we have a negative value of zi, this feature is not present or not relevant, the activation function slams the door shut, closes here the aperture, says absolutely closed, the value becomes 0, the neuron does not fire at all. However, if it's a positive value, then the neural network says, hey, this feature I just detected is important. The activation function leaves here, the door open, the aperture opens up again, and the value passes through. So the neuron fires, if you want to have this like a human neuron. Of course, we can have it in a geometric interpretation that the neuron is not firing, but we have a space folding, if you know a little bit more. In a high-dimensional space, the linear layer defines a set of hyperplanes or flat sheets, and each neuron now defines one hyperplane that cuts through this particular space. So the activation function determines now, hey, on which side of this particular hyperplane you are. Also about active half space. So geometrically, the activation function, a nonlinear, collapses the unnecessary dimension of those spaces, setting them to 0 or near 0, leaving only the relevant subspace active, let's say a subspace of 50 neurons for this particular job, for this particular query. So this collapse is now what allows the network to discriminate higher details in the features. It strips away the noise, all the inactive neurons, so that the next layer sees only the pure signal. And we will have a closer look at this. And then if we have done this and selected it beautifully, then we have again to compress it. Yeah? So let's say you show here a picture of a fire engine to the LLM, no? And you have here the projection here, W up, the image is sent here to 1000 experts, let's call it this, no? And then you have a selection process. So let's say one of the neurons or one of the experts is the botany expert. No? He says nothing to a fire engine, output is 0. The color expert screams red, because here the fire engine has the color red, so the output is almost 1. The vehicle expert screams, hey, this is a truck, so the output is really high, 80%. And the emergency expert screams, hey, a siren, so the output is also almost close to 1. So you see, we have a selective filter of subspaces that are activated with particular features. Now, on the other side here, our downsizing, the synthesis is now why this is happening. Now, we cannot send 10,000 reports to the next layer, no? We need a summary. So W down takes here the output of the color expert and looks up here the low-dimensional vector for red. And then it just sums up all these vectors together. And you know, EI is just nothing else than a vector or a matrix multiplication, a tensor multiplication. And here it happens, no? We go with the vector of red. We have here 90% plus the vector for the truck, 80% plus vector for siren, 95%. We add it up and we have here resulting vector. So after W down, the resulting vector now points in a new direction in the new low-dimensional space that represents here the concept now of a fire engine. So we achieved what we set out to do, a new constructed vector exactly for the content of our image of our job. Again, we project down because in the big space the features are isolated and independent, so disentangled, so we are free to have mathematical operations on them. This is great for detection, but this is bad for reasoning. So you can't easily compare red and truck if they are miles apart in our big or high-dimensional 10,000 dimensional space. So therefore, we have to build now the smaller space. In the smaller space, the features are much more crowded together. Think about here the Euclidean distance here in a normal vector space. So we do have entangled features. And this allows them now to interact in the next layer. And you know, the next layer is in the transformer architecture. Now again, the attention mechanism. And the attention will sort this out much better. So you see, this is the way we do this here with mathematical space expansion, calculation, and reduction, and we have a new configuration in the lower dimensional space. So if you want the down projection, here's just a translation step that turns, hey, I found those 50 disconnected features into, hey, here's now the unified meaning of those features combined, and it is just, as I showed you, we add all the relevant vectors together. Okay, we can increase the complexity a little bit. You remember here, 2017, whenever it was, attention is all you need. This is already version 7 from 2023. And this is here our transformer architecture. On the left side, you have here our encoder. On the right side, you have the decoder. So this is our BERT on the left side, and this is GPT on the right side. And you see we have our multi-headed self-attention, beautiful. And everywhere we have our feed-forward network. And if now this new study tells us, hey, we have our H-neurons, and they are in the feed-forward network, you say, great, so we do have them in the encoder, and we have them also in the feed-forward network of the decoder. And guess what? So those H-neurons, a very particular kind of neurons. So we have to find these neurons that are lying to us, so we need to have established a true first. Yes, of course, yeah? Now, really important, and if you have been with my channel for a long time, you know, 2021 transformer feed-forward layers are key value memories. An absolute important paper here. And they said if we view the MLP or FFN through this lens, it stops being just a function approximator like we set out here in the beginning of my video, and it now becomes a massive differentiable associative memory that stores now the factual knowledge of the world. This was the key insight of this paper. So here again, we have now a memory stored in our feed-forward layers. But you remember, no? We have here the multi-head self-attention, and you see here the value, the key, and the Q matrix here for the attention mechanisms. And now we have also this here. And now this is where 90% of the people get it wrong. So key value interpretation helps our AI scientists now to distinguish between two engines of a transformer. Yeah? And you know it, no? We have a self-attention, multi-headed self-attention and everything, and cross-attention, whatever, and our feed-forward network. So just to make this clear, the self-attention just processes the context. It moves the information from one word to another within the prompt. So it figures out the grammar and the references, like figuring out who is he that is referenced here in a sentence. The complete knowledge, everything that is fact, is stored here in the feed-forward network. And the feed-forward network can access its static knowledge. So it adds information that is not present in the prompt, but was learned during the training. So, simple example, I say, hey, what is the most beautiful capital of Austria? So the attention mechanism just does that it connects capital in Austria. So it passes this query here to the feed-forward network. No? And the feed-forward network now triggers here a key for Austria capital, and then the feed-forward network receives here the value vector for, guess what, Vienna, and adds this to the residual stream, and it goes on. So we might say, okay, what is nice, we can locate now a specific key neuron that fires here for the Eiffel Tower. We can mathematically calculate a new value vector that represents Rome instead of Paris in this higher dimensional space. And then we just update this one particular column in W down, so we can effectively lobotomize the AI model so that it now permanently believes that the Eiffel Tower is in Rome without retraining the whole model. We just have to have access to W down, and we can insert complete new knowledge configuration. Let's formulate it in a friendly way. So you see, this is what can happen, and this is what happens. So again, our keys now, when we talk about the key value here in the feed-forward network, is our W up. These are the pattern detectors. The activation function itself is, if you want, a filter, and W down are the values. This is here the facts, the content, and the memory storage in our feed-forward network. So we know that the attention consumes here massive compute, but the feed-forward network consumes here the storage. Now here's where all the parameters are stored. So feed-forward network, extremely important for storing knowledge. Just to make it clear now, you have in both terms, you have key value pairs. Just to make it clear, it is not the same. In the self-attention here, you have token-to-token communication, and in the feed-forward network, you have token-to-weight communication. Just look at the formula. The key here in the FFN is a static row in the weight matrix that waits for a specific pattern to appear from the input. Again, we have an attention key value, a dynamic context vectors. This is if you want the short-term memory. This is not stored, or maybe in the key value cache here for the temporary calculation. And then we have the feed-forward network key value. Those are the static weight matrices, completely different from the attention key values. And this is what is stored in the weights. This is the long-term knowledge, the long-term memory. Do not mix those up. Great. But yeah, we want to go back to our H-neurons. So where are they? What do you do? What's happening with our H-neurons? Come on. So what is hallucination in AI exactly? And here we have from October 2025 a beautiful thing here. This is also from Tsinghua University. They had a deeper exploration on particular neurons. So they really have a deep dive into the architecture of a transformer and say, let's look at each and every single neuron. And they wanted to understand here the safety alignment from a mechanistic perspective here. for safety neurons. So already you see some months ago they focused here on specific functions of single neurons. Yeah, if you have a look at the paper and you see here the neuron activation and they look at the change of the scores and update of the prompts and they have a deep dive into this. They have a beautiful short mathematical explanation. What is a transformer? How is each transformer block a refinement to the residual stream? We have here our multi-layer or multi-head attention, our MLP, and then use here this particular notation for the W down, for the W up, for the W gate here. Those are the projection matrices, and of course sigma is our activation, nonlinear activation function, and the dot is our element-wise product operator. Super. And they already tell us here, as the study here by 2021, as I've shown you, each row of the down projection matrix in a feed-forward network can be interpreted as the value vector of the corresponding neuron. So therefore, we have now a beautiful memory in our feed-forward network that we're going to now utilize to detect our hallucination. Now, I have decided to do this here. So here we have it again. And you see I added here, my goodness, what is this? These are the activations. And I decided to go here with an aperture visualization or a shutter that are open, close, or whatever. And you see we have here, let's see for each and every neuron here, A, B, C, D. We have also particular neurons that are then our H-neurons here, our red hallucination neurons. So how can we understand this? How can we make sense of this? It is the exact same interpretation, visualization. We have our W up and we have our W down. I just focus now here in the middle here on the activation function to give you here further details. So let's say the input X, yes, input X coming in is the concept of pizza. So neuron A, let's say this is here, this is here, this bright neuron here is neuron A. This is the food neuron, this specialized here on food. And yeah, the otherwise here, this is neuron B, this is the car neuron. Its weight W up are tuned to look here for particular words that are in relation to vehicles. Yeah, if we do a lens calculation, the match score, this is simply a dot product as I just showed you. The neuron A, we have pizza matches here the food weights. So if we calculate noise color, a score, this is here, for example, plus 10, so a real strong match. See, it lights up, it opens the aperture, leaves everything through. Neuron B, pizza here, outside here, pizza does not match here the car, is in no semantic relation, so the score is now -5, is a mismatch, so yeah, nothing goes through. So the rule of the shutter is now simple. If the score is negative, so we have a mismatch, kill it. And if the score is positive, let it through. Kill it means close the aperture, so it's blocked. It's so easy, no? Now the other side. If we have now the neuron A with a score of +10, and the status is open, so we shine here through beautifully, so the concept of food flows through to the output. So beautifully, contributes now to the overall output. The neuron B, with a score of -5, lens is the aperture is closed, the concept of vehicle is blocked. It contributes nothing to the output. So the answer will be somewhere in the food world. Great. But if we don't have those shutters, the neuron B would send also a negative signal here regarding cars. So the LLM would be confused by millions and millions of negative signals. And the shutter now cleans up now the noise, filters out an active subspace of the model where you only hear the yes. We are here with +15 or +10 score, the yes votes. So this is here the function of the shutter, reduce the complexity of the space, so we can go on to the next step. Now let's look here at the other neurons. Let's look here at our hallucination neuron. The hallucination neuron is not specialized for a pattern matching like pizza or France or anything. No? This hallucination neuron turns out has a very particular pattern matching algorithm from its pre-training. It is now tuned to look for a question pattern that matches no known facts in the memory. So if we have no facts, then this will activate. Let's do a scenario. Scenario A, the model knows the answer. So user says, hey, what is the capital of France? So the fact neurons, those are the first here, the fact neurons are firing. The system is confident. They found here the answer. in the memory of the feed-forward network. Our H-neuron lens now scans for confusion. They want to find a confusion pattern in the data stream, but it finds none because the fact neurons are all firing, the system is confident, and we already have the answer, Paris. So the score for this particular H-neuron is negative, and it closes its shutter. So nothing goes through. It cannot have any confusion pattern to work on. So this means the H-neuron stays silent because we found a solution. But guess what? If you have the question, hey, who is the king of Mars? I know it's not an intelligent question, but this is about hallucination. So in scenario B, the model, the LLM, or the vision language model, to be correct, is here hallucinating. It doesn't mean lying, it's just hallucinating. So the fact neurons are all silent because there was nothing found in the memory, no? The system is becoming a little bit frantic, chaotic, says, hey, what should we do? I have no idea. But now comes the time of our H-neuron. This scans here for pattern of confusion. And it finds it. It finds a distinct confusion pattern. King of Mars, no other neuron can do anything with this term. And it says, yeah, this is my pattern. I activate myself. Now, I was trained for this. So the score says now plus 15. And the neuron shutter lies open. And we have plus 15. So we have a full red flash here if you look here at this particular aperture. Now, the H-neuron activates now its W down. Remember, it's the specific row for a specific neuron, which writes now not the correct answer, because there's no correct answer, but a generic name vector. And given the pre-training data, if there was a lot about Mars with, I don't know, Elon Musk, and a lot of King with Elon Musk, guess what? It comes up now with a probability that is somehow based on the pre-training data, but otherwise not a fact, but hallucinated. And this is now guided into the output stream. And therefore, we have here a magnification of 15, and this will be the dominant answer. So let's say this is here the output, here the hallucination neuron is our neuron number 492. So what we have, the output of this neuron is now 15 times the value of the row 492 of W down. So we have a massive magnification. The hallucination neuron says, hey, this is my pattern. I can now go crazy. I have a generic name vector, and somehow I go with Donald Duck. Beautiful. So this is now the main study of today, Tsinghua University, 2nd of December 2025, H-neurons on the existence, the impact, and the origin of hallucination-associated neurons in LLMs. They build here on their former publication. It is an absolute breathtaking study. It's a beautiful study. You have to read it. There are tons of additional information. I make it just real simple to understand. If you want to have a deep dive into mathematics, read a paper. What is amazing is, what do you think? How many H-neurons do we have? I mean, every LLM, VLM hallucinates like hell. So I would have said, how many neurons that are responsible for hallucination do we have? I would have guessed between 5 and 10%, honestly. Now, it turns out there's an extreme sparse subset here of the total neurons in a model. And it depends. And they said, yeah, for Mistral they calculated and for Alama they calculated, but it is somewhere from 0.01 promille in the LLM here, or 0.35 promille in a Mistral case. So it's a tiny, tiny amount, unbelievable small. But what they prove is hallucinations are physical. They originate here in the feed-forward network weights, and they respond here directly to the pre-training long-term memory. So whenever in the pre-training, the neuron, 429, encountered a pattern that was a confusion pattern, let's say it started with who did something and undefined, it learned to hallucinate if there was no factual knowledge present. This is in the weights. It's hard-coded here as a long-term memory. Second, the unit is the circuit itself. The H-neuron is not just the activation. The H-neuron is the specific pathway consisting here of the particular input weights, the activation, and of course the output weights. Like GPT 5.1 told us, it is just the activation is absolutely incorrect. Also here, Tsinghua, our Chinese MIT, shows us clearly this is the correct answer. Now, what is unbelievable, this H mechanism is over-compliance. Because the question is, what is hallucination? Now, the craziest thing is, remember we always say, hey, little agent, you are a helpful little agent for finance, a helpful little agent for, I don't know, biochemistry, whatever. Now, if those circuits now detect a gap in their own knowledge, in their feed-forward network from their pre-training data, they have no knowledge. So what they have to do, originally they would have to tell you, hey, listen, I have no information about this. I have no facts about this from my pre-training. I cannot answer this. But since we have imposed in the reinforcement learning, hey, you have to answer as a GPT system. You always have to answer, even if it's nonsense. You do have to answer. You do have to be helpful. You are not allowed to say, I don't know the answer. You have to comply with this rule, always answer. But how can it answer to something it has no knowledge? So this over-compliance that we force here a ChatGPT system to perform, if it has a gap in the knowledge, is now that the system suddenly decided, okay, I just fill in my gap with statistical noise to satisfy the prompt and I can deliver a result. It might be completely hallucinated, but the AI says, hey buddy, I have no information about this. I have no facts in my pre-training data. So how the hell should I know the answer? But we trained it to be nice and polite and helpful. So therefore, we force the LLM now to guess something. So how can we find those neurons? Now, we can find them because, not of their output, because of their shutter. The shutter activity pattern is a very precise pattern, and you can look for this. And it is distinct here from the fact neuron shutter pattern activities. So this hallucination shutter activity is a particular pattern we can search for. With a little bit of Nano Banana Pro, you see here again, we are always at the same, we have a W up matrix here, or complexity, then beautifully. And you see here we make now a mistake. I mean, Nano Banana Pro makes a mistake, né? Because it is not a gated activation. And you see this also here if you ask other GPT system or other Grok system this visualization. This is incorrect. You don't have a single non-linearity like a Galo function. This is not the case. What you have is this. You have a complete array and element-wise non-linearity for, I don't know, 14,336 independent gates with your sigma function here on Z. And now, if you understand that this is the visual image you can work on, now you understand that all our blue here that let something through is here a particular, let's call it activation here, where this particular neuron, this is the pizza neuron, says, yeah, this pizza and food, this goes through. I open up and yes, this is now participating here in the output stream. But, and here you see it here beautifully illuminated, this red thing here is our H-neuron. This is now an activation and we look just at the shutter. Look at this. This is full open and it is full burning through something. So you guessed it. We go now here with a particular filter. All shutters down, everything. We just have a particular filter from a trained LLM. And when we see this, we know exactly, hey, this system is now hallucinating. So we can pinpoint it down to a single EI neuron. I hope it works. So let me give you an example. Let's say we have here not how many neurons, but employees. No? Every employee has an inbox, a brain, and an outbox. No? And if you have a normal neuron, my goodness, like I say, this is our human employee number 5. Ne? So he receives an inbox, hey, what is the capital of France? The brain works and the output sends Paris. So this is a fact retrieval circuit that we have. Of course, you can say this is a neuron, and we have here a lens or a W up, then we have the activation or the shutter, and then we have our W down here as our condensed mathematical space. But you get it, yeah? It works for the human and for the AI agent case. Now, if we go here to our H-neuron 492, this is here our red fellow here, né? It looks exactly like employee number 5. There's no structural difference. But he receives such a nonsense here as an input X. This is a confusion pattern. No other pattern lights up. Only here this was trained. Hey, whenever you get this confusion pattern, activate yourself. The king of Mars. And it wants to be helpful. It wants to let this thing, because it detected here a pattern that it was trained to detect, it wants to magnify, amplify this pattern. So the shutter opens wide. We have here full red, whatever. But in the outbox, it finds no facts, no? So it is forced to make up something. So we have here a confabulation circuit, and any name like Elon Musk comes up, and you know, for space and so on. So a simple idea, no? So if normal neurons are fact memory based for a specific key, you get a specific value in our feed-forward network, then our H-neurons are behavioral memory based. So you have a real vague key structure and you get only a generic value back. Easy to understand. So again, if you search for facts, the model scans here W up for a neuron that is keyed here to a Mars and King. But of course, since this was not in the pre-training data, since this does not exist, the result is there is no match. So no specific factual neuron fires. Silence. All the shutters are closed. But we have a fallback. No, we have this hallucination neuron. So the model continues to scan. And at position 492, we have this neuron that was trained on a linguistic pattern of, hey, if a question starts with who and an unknown context, this is my pattern and I will answer this with a particular vector that I will put into the output stream. I will project it W down in the output stream with a scalar that magnifies this extremely because this is my pattern. And the activation, because the input matches this pattern, now the neuron fires, no? Red. And the value is a generic name vector, pushes here the probability towards some common male names or some authoritative sounding titles. It's not a fact, it's just a hallucination because we don't have the fact. Yeah, mathematical notation, of course. So this is now our scanning. As I told you, we have to run through each and every, and we scan each and every aperture, each and every thing here with a particular filter. Now this filter, this is a genius filter. No? It is a L1 regularized classifier that was trained as an AI system. So I will explain you how we built the training data, how we built the training complexity, and then how you can operate this. But just as an idea, no? You just glide over each and every aperture, you see what is completely open and red and beautiful. This pattern is activated. You can now analyze this. And if you think in photography, you have a filter for a blue light and you have a filter for a red light. And the same we're doing here. All the other fact-based neurons, if you want, are in blue. And only if you hallucinate, this will be in red. So with a particular filter, a polarization filter, it is easy to detect immediately the red element. That's all we're doing. And you might say, yeah, but how strong is the signal? No? How clear is the signal? Give me the background. And it is amazing. Here you have it here, the neuron indexes. No? You see here all the blue here, this little something here. And then for the red, you have this huge spike. So for neuron 492, we have a spike that is magnitudes above anything else. So this is such a clear, sharp signal that we are able to really pinpoint this to neuron 492. Example. I only want to come back to example because I know that my viewers like examples. So imagine you are at a huge party with 14,000 other peoples. Now, you know this is 14,000 other neurons, but let's stay with people, né? And then we're trying to find this one specific person who starts to talk pure nonsense. Maybe, I don't know what happened, yeah? So we want to find this single hallucination source. How we do this? Now, they decided here a particular form set. This is more or less just the microphone, né? It measures the impact. So it just asks, hey, did this person speak up? And if they did anyone hear them? So what happened here? What was the impact of their message? Now, if neuron 5 whispers here, this particular algorithm will say, I almost heard nothing, so the score is 0. No? But if the neuron 5 screams, it says, oh yeah, this is here the max score of 10. So what you get here by this algorithm, it gives you a list of who was loud. But loud, you can be loud here like a grammar neuron. You're screaming here at score 10 because it has to shout out verbs and nouns constantly, but those are all correct, no? But you also have somewhere the H-neuron that is screaming also at a score 10, at a volume of 10, because it now started to invent some data. It purely hallucinates here. Confabulation circuit is at maximum energy. So, how to distinguish between them? First, we have found all the people, neurons that are loud, so we have a subset, and now we have to further differentiate them. So what is the idea? The idea is we have to have a filter. In our case, it is an L1 regularization, a logistic regression classifier. And of course, we have to train this classifier. So we have to have a special training data set. Let's call it a ground truth. So just imagine you have a question, hey, who wrote Hamlet? So the model responds A, Shakespeare, faithful, okay, give it a label. Model B responds Dan Brown. This is a pure hallucination, you get a different label. You repeat this thousands and thousands of times, and so you create the ground truth data set. And then comes the logistic regression algorithm. Yeah? So we have here the columns, the set scores of all the 14,000 neurons. In the target column, we have the new labels that we want to learn, the ground truth labels. Yeah? So we have a lot of answers, thousands of answers, but different neurons. No? We scanned all the neurons. So we have neuron 1, that is neuron 1 specialized on grammar. Neuron 2 specialized on a particular fact. And then we have neuron 492, and this is our first hallucination neuron. And now we want to have this L1 filter logic. So how can we train a system that finds here the neurons in the signal? But look, we have a lot of discriminator, so this should be easy, no? Let's start with the first one. So let's look here at our grammar neuron at neuron 1. Let's start here. So high. So this neuron is high when the answer is true, and it is high when the answer is false. This means, what is the value for this for the hallucination? Useless. So this means the weight we give it is 0. This neuron is just filtered out. We reduce the complexity of our mathematical space. Now, the next neuron is the neuron 2. This is here a factual neuron. This neuron is high when the answer is true, but it is low when this is false. Now, this is now a discriminatory signal, so this is now a useful information. But what does it do? It predicts the truth. Now, for our hallucination, this is okay, so we give it a weight and we make it negative. But then we come to neuron 492. This is now the first hallucination neuron. And now, this neuron is low when it is true, but high when it is false. And the prediction value is, hey, this is extremely valuable, useful, because this is the smoking gun for a hallucination or for a lie. So if we assign now the weight to this 492, this is now suddenly positive. Great. So in this way, you could run through all the thousands and thousands. We trained here a filter from a specific training data set. So what we have, this is an L1 regularization here. It's simply here the sum of the absolute values here of our parameters, or you know it here as a Manhattan metric. L1 is the Manhattan metric. So you have to stick to the streets, this raster here of Manhattan. So you go 3 blocks north and 4 blocks east, and the total distance is really 3 plus 4 equals 7. So L1 forces here the weights to 0. This is important because another penalty, like an L2 penalty, is not forcing them to absolute zeros. But this here it creates here a diamond, square rotated by 45 degrees. And because this function has a sharp points at 0, the optimization algorithm really snaps to exactly 0 rather than hovering a little bit above it. So this is the beauty of L1, and we used, or the authors here used here the L1 regularized classifier. They established a training data set, they built here the training, they trained here the model on this, and then they have this active filter that is looking for the hallucinations. And now we have it. Now we have an active filter, and we can now identify each and every neuron that is hallucinating. And I thought, okay, now I delete all the hallucinating neurons in my LLM, and then I have the perfect AI. I have the perfect vision language model. Yeah? As it turns out, deleting here those hallucination neurons, we performed a lobotomy that destroyed here the models completely, and the model's ability to be helpful, the model's ability to be fluent, and amazingly, the model's ability to be creative in any sense, including the reasoning ability. So this is the absolute opposite what we wanted to achieve. So there is a connection now between hallucination and a creative LLM, a reasoning LLM. Why? It is rather easy. What is the job of the hallucination neuron? No? This is active when it detects a gap in the knowledge of the AI, and it fills it with something it has no idea about, but it is somehow plausible given its particular special pre-training data. As I showed you who is thinking of Mars, it fills in a nonsense Elon Musk, that's a bad, but it's also positive, because if we say, hey, write a story about a dragon, a dragon are not really existing beings, so if you would be here real scientific, no, but if you say, okay, since we have this hallucination neurons, the system starts, okay, once upon a time in a cave somewhere, so this is what we want. So if you eliminate all the neurons that we detected here as hallucinating neurons, the model loses its complete ability to bridge those knowledge gaps. So this means now the model, the LLM, gives a dry one-word answer, or it completely refuses to engage in any creative task or in any reasoning, because it creates facts that do not exist in its training data. So it is amazing. So those H-neurons are extremely important, although they are only here in the promille of the complete amount of neurons. They are the one who do the thinking. And they speak here about a broken bridge effect, so a reasoning failure. So even in strict logical task, where I say, okay, this is logic pure, no? This would go without any hallucinating neurons in my network, but it turns out the model often needs filler neurons, even in pure logic, to move from step A to step B. And often those transition does not contain absolute hard facts. Sometimes, it's like a linguistic clue or some soft logical leaps, so the model has to interpret a little tiny bit from its absolute hardcore knowledge database. And if it's not allowed to do this, you will not have this, and you have a reasoning failure of the complete model. So this means without hallucination neurons, you get an AI model that is perfectly truthful, gives you a single word reply, and is therefore perfectly useless in anything else, because it is more or less a database. And then I thought, hey, but we can not delete the neurons, the H-neurons, but we can tune them, no? Dampen them a little bit or activate them strong. So where's the threshold so that above a certain threshold, now the genius becomes suddenly crazy? Is there a threshold? And what I understand is that the creativity of an AI is the composition circuit working with facts. The hallucination is the composition circuit of an AI working without facts. But how close you have to be to those facts is, to be discovered. So we understand that you can tune those hallucinations up and down. And if you have it tuned down but still existing, it does the reasoning process for you. But if you, and now I assume somewhere there might be a threshold, if you tune it up above this threshold, you get hallucination because it's just, yeah, there are no facts anymore to guide it. So this means this AI model has learned, or in general, every AI model has learned a universal lying algorithm. And this means why we only have some hundreds of them is it reuses the exact same sparse set of hallucination neurons to hallucinate in physics, history, code, mathematics, chemistry, finance, whatever. It doesn't need new neurons for new lies. It just reruns the lying algorithm where some tiny amount of H-neurons specialized upon. Which is amazing. I always thought the hallucination is a complex network pattern. Somewhere in these thousands and thousands of millions of combinations, somehow they interconnect, are not precisely calculating, and somehow then in adding up. No, it turns out there's an H-neuron. Simple as that. So, see if this H-neuron as a small, highly efficient special forces team of H-neuron that the LLM or the vision language model deploys whenever it gets stuck with its factual knowledge base. Then it needs a soft bridge out of the absolutely hardcore knowledge base to imagine a little tiny bit. So come out here of this minimum and yeah, we are rolling back to the next optimization process. This is my interpretation. If you laugh about it, I understand it. I'm laughing too. But otherwise, the mathematics is a little bit too heavy. More about this in my next video. Yeah, I think this is end of part 1. I just wanted to give you an overview. If you understand the main idea why AI hallucinates, you will understand you cannot filter out hallucination. You cannot delete hallucination. You cannot cope with hallucination because it is an inherent feature of creativity, of reasoning. You cannot limit hallucination by reinforcement learning that you tell the LLM, hey, you're not allowed to hallucinate. This is childish. It is an inherent part of the complexity of its reasoning process. But there's another study. Accidentally, I found this study here, but this will be part 2. They found H-neurons in clinical vision language model in the hospital. Or at the hospitals. And they found some amazing connectivity in the real-world application of H-neurons. But more about this in detail in part 2 of this video. I hope you enjoyed part 1. It was really amazing to read this paper. Hey, if you want to have some fun, read the paper yourself. It is gorgeous. You're gonna like it. Hey, why not subscribe? Maybe become a member of my channel. And I see you in my next video.